When it comes to calculus with parametric equations, another thing that can happen that's very interesting is we can not only have horizontal tangents indicating extreme values, but we can also have vertical tangents as well. So we look at the individual components and their derivatives and see when those are zero. So horizontal tangents, if we're looking for those, we look where dy dt is equal to 0. And that might seem a little counterintuitive, but just kind of think of the equation of a horizontal line would be y equals a constant, so it's dy, telling you about horizontal tangent lines. But then also, if you think of the original derivatives, they would have been dy dx, and those would have all been horizontal, so the y is in the numerator. And then vertical tangents, of course, would be the opposite. So that's where dx dt would be equal to 0. So let's take a look at a curve here. And I have x equals t squared minus t plus 2, y equals t cubed minus 3t, and t is on the entire domain from negative infinity to positive infinity. So we want to find all possible horizontal and vertical tangents. So let's try this out and see what we can do. So we'll begin with locating horizontal tangents. So we're looking to where dy dt is equal to 0. So that really tells us that we need to first find the derivatives of these component functions. So x prime of t, the derivative of the x component would be 2t minus 1, and y prime of t would be 3t squared minus 3. So if I were to take the y component's derivative, 3t squared minus 3, and set that equal to 0 and solve, that would tell me the location of any horizontal tangents. So let's see. I've got a common factor of 3 I can pull out. And then the difference of squares, so this could be t minus 1 times t plus 1 equals 0, so that t is equal to positive 1 or t is equal to negative 1. So these are t values for where critical values would occur, so the locations of horizontal tangents. Now, vertical tangents, we let dx dt equal 0 and solve. So I have here 2t minus 1. If I set that to 0, that would give me 2t equals 1, or t equals 1/2. All right, so these are the t values where this happens. These aren't the actual coordinates where they're happening. So to get the actual coordinates, we have to take the t values and calculate the xy ordered pairs to see where that's happening on the graph itself. So for instance, if I have positive 1, negative 1, and 1/2 as my t values, then if I plug in 1 to the x component, that would be 1 minus 1, which is 0, plus 2, so has an x coordinate of 2. And then if I put 1 into the other function, that would be 1 minus 3, which would be negative 2. All right, so 2, negative 2 should have a horizontal tangent. Then at negative 1, that would be 1 plus 1, which is 2, plus 2 more would be 4. And if I plug negative 1 into the y component, negative 1 cubed is negative 1, and then it would be plus 3. So negative 1 plus 3 would be positive 2. And then when I put 1/2 in, I've got to do a little bit of work with fractions, so I think I'm just going to let you trust me that it is 7/4 and negative 11/8. Okay, so let's take a look and see that this is the case. So I am in parametric mode. So again, if you're not in parametric mode, change your calculator to that particular mode so that when you go under y equals, you can provide an equation for both x and y. Now, let me get rid of what I have already. And then I have x1 as t squared minus t plus 2 and y as t cubed minus 3t. And I should set the window, okay, I'll set t from -10 to +10. That should be sufficient. Let's take a look and see if we can identify all the pieces here. Okay, so here is the graph. It does look a little bit funny, but let's see where these 3 points are that we located. So to graph a few points on this, I need to go under, I think the easiest thing to do is to go into the list editor and then just add in some points in L1 and L2. So I'm going to put the coordinates here of these points. I had 2, 4, and 7/4 for the x. Then the y values were -2, +2, and 11/8. So I'll just enter those as ordered pairs and turn on a stat plot so that I can see those points on the graph. Oops, it looks like I've got one in the wrong place. I bet I mistyped in one of the points, and you all probably found that while I was doing it and were telling me as I was doing it. Looks like this point here should have been -11/8, not +11/8. So that's the problem. So let's fix that and try again. There we are. So now we can see where we have these points here. We have a good representation of where horizontal and vertical tangents are occurring. And it might be instructive to zoom in on that particular region. So let me just do like a zoom box. Okay, so the zoom boxes take forever to do on screen here, so I'm going to save you all from having to watch that. But you can see here, I can, the uppermost point here to the upper right, you can definitely see a horizontal tangent going through there. The lowest point here would have a horizontal tangent there, and then a vertical tangent at this other point. So that definitely meshes up with exactly what we found algebraically. All right, let's try another example. We want to find the first and second derivatives of the plane curve and then locate any critical values that are on the graph. So first and second derivatives, so we'll start there. So the first derivative is always pretty straightforward. It's dy dx and is literally the derivative of the y component, which in this case, the derivative of y would be 2, divided by the derivative of the x component, which in this case, the derivative of the x component is 2t. So this results in just 1/t. The second derivative, however, you've got to be very careful. It's the derivative with respect to t of the first derivative, which I'll just go ahead and write as t to the -1, and then divided by x prime of t. So the derivative of t to the -first power with respect to t, we would bring the exponent down as a multiplier and subtract 1 from it. X prime of t is 2t, so it looks like I have -1/2t cubed when I simplify. All right, so that gives me the first and second derivatives. The next thing that I want is the locations of critical values. So critical values are places where we could potentially have minima or maxima, but we're not labeling them as such. So the critical values, that could be the places where, in this case, either the y component, the derivative of the y component would be 0, or the derivative of the x component would be 0. So we set each of those derivatives to 0 and solve. So if I set the if I set the x component to 0, that would be 2t equals 0. So t equals 0 is a critical value. And for the y direction, if I set 2 equal to 0, well, that doesn't make any sense because it's a contradiction. but it just means that there's no additional critical values from that. So t equals 0 would be the only critical number. And one more example here. We want to do the same, find first and second derivatives of the plane curve and locate critical values on the graph. All right, so this curve you should recognize from the previous section as a circle. All right, and so a circle, you should already know there would be 4 critical values, so 4 places where we can have horizontal and vertical tangent lines. But let's see if the math works out that way and tells us that. So we'll start with the first and second derivatives. So dy dx is going to be y prime of t over x prime of t. Y prime, if I take the derivative of 4 sine t, that's going to give me 4 cosine t. So that's the numerator. The denominator, the derivative of 4 cosine t is negative 4 sine t. So negative 4 sine t. The 4's cancel. There's still a negative, and cosine over sine can be simplified to negative cotangent. Okay? Then the second derivative, d squared y over dx squared, that's going to be the derivative with respect to t of negative cotangent of t all over x prime of t. So the derivative of negative cotangent, so that's going to be, let's see, the derivative of cotangent is negative cosecant squared. So put that in. I have a negative out front because there's a negative on the function itself. Then its derivative is also negative, so those will cancel. X prime is negative 4 sine t. All right, so all these negatives actually result in a final answer that's negative. And then I have cosecant squared t. Then it's divided by sine, but if you divide by sine, that's the same thing as another factor of cosecant. So really, oh, there's a 1/4 in there, I'm sorry. So really this is negative 1/4 cosecant cubed of t. All right, so there's our first and second derivatives. The last thing we need to do is find the critical values. And just like we did in Calc 1, in order to find critical values, we just take a derivative and set it equal to 0. But in this case, we have effectively 2 derivatives. We have dy dt, which is when we set that equal to 0, is going to find horizontal tangents for us, and dx dt, and when we set that to 0 and solve, it will give us the location of any vertical tangents. So let's take each of these and see what happens. So dy dt is 4 cosine t. When I set that to 0, first thing of course I would do is divide both sides by 4, and that gives me cosine t equals 0. So effectively I just need to take the arc cosine of 0 and find out any points where the cosine of t is 0. So that's going to be at pi over 2 and 3 pi over 2. And of course, if you need to review a unit circle in order to find those, that's fine. Dx dt, that is negative 4 sine t. When I set that to 0, divided by the constant to get rid of it, I'm now looking for where sine of t is equal to 0. And that occurs when t is equal to 0 and pi. So we've got 4 locations here. And if you think about this curve that's produced by this set of parametric equations, that should make sense because it's going to be a circle. And in particular, it's a circle of radius 4. And a circle of radius 4 is going to have 4 places where we have horizontal and vertical tangents, and that's going to be at an angle of 0, at an angle of pi over 2, at an angle of pi, and finally 3 pi over 2. All of the values that we just came up with.